Okay, so this is week 2. We are going to be discussing a few concepts like basic continuous time signals and basic discrete time signals. And objective 3 will to do some classification of systems. Of course, definition of systems, and then some classifications of systems. So that is our subject for today. As I mentioned yesterday, we have a GA who I will ask to do some examples and tutorials with you. Of course, I can also plan, but as I mentioned, we needed to move with some speed because we have started the lectures late. So our lecture starts here, where we need to talk about a few or the basic continuous time signals. And to start with, we are going to start with the unit step function. And as the name suggests, it has a unit value after time t is greater than 1 or than 0. Sorry, and of course it looks like you are stepping on a step. If someone was here, then they would appear like they are climbing a step. So in few words, that is the illustration of a step function, and it may be shifted in time such that at times, okay, this one is not shifted. This is not shifted. This is shifted in time. So when we say not shifted, we are saying that the step is starting at time equals to 0. But if it is shifted, then the step is occurring at time bigger than or okay, not equals to 0. So that is the basic definition of a step function, okay, like illustration. But then in mathematical format, you define step function as equals to 1 for t is bigger than 0, and is equals to 0 for t is less than 0. So as clearly as you can see, before time is 0, our step function has 0 value, on this side, but then beyond time t is equals to 0, the value of our function ut is equals to 1. So again, in very few words, or in very many words, that is how you define the step function. And it has another name that we call Heaviside unit function. So that is an alternative way you can express your ut. So, and the symbol will be used for step function is ut. So again, you need to get used to, so when you see ut or u function of t that is shifted, then you can always know that that is a step function or unit step function. And as for the sake of illustration, I have said that a shifted unit step function has value equals to 1 for t is bigger than t naught. So that is the alternative definition, when it will have value of 1 for t is bigger than t naught. And it will have a value of 0 for t is less than t naught. So as expressed at that point. The last thing I want to mention is that as contrary to what may appear here, at t is equals to 0 or at t is equals to t naught, the value of u or step function appears to be equal to 1, but as a matter of fact, it is undefined at this point. We actually don't know what the value of the unit step function is at t is equals to 0 or at t is equals to t naught for the shifted value. So that is a major point that you should become aware about, that that u or unit step function is not defined or is discontinuous at time t is equals to 0. And carrying on, we can now define the unit impulse function, which is also referred to as Dirac delta function. It is symbolized as delta t. So this symbol, we call it delta. So, and we draw it just like I'm drawing. It is not that, because you normally use this one for partial derivative or partial derivative. So this is not that one. It is not d, but rather it is just that symbol that takes that shape. It's called delta. It's a Greek letter called delta. So we are saying that that is the symbol for the unit impulse function, and it is also called delta function, and it plays a very central role in system analysis. And traditionally, it is defined as the limit of suitably chosen conventional function having unit area over an infinitesimal time interval, as we are seeing in a diagram here. So we are saying that this is a conventional way of representing the delta function or Dirac function, and we are saying that for a very small length, okay, well, what do you call it? For a small value of dimension that we symbolize with e, the e is approaching 0, we say that the Dirac function is having the value as illustrated by this diagram. And if you are to calculate the value or the area of this graph as it increases or as e approaches 0, the value or the area under that graph is equals to 1, or unit to it is equals to unit or unity. So, well, that is a conventional way of illustrating, but in mathematics, it takes a different value altogether. Like it's considered to be a value that is not defined, like at time is equals to 0, d of t is considered to have a value of 1, and its height appears to approach infinity. So you're saying that height of that graph of that arrow appears to approach infinity, but the area that is defined by this arrow that represents a unit impulse function, it has a value of 1. So in mathematical form, in how you define it, for time varying t, if t is not equal to 0, the value of the function delta t will be equal to 0. And for time is equal to t, this height, the height of this graph is approaching infinity. So the one I'm drawing here is more or less representing the unit area that I was mentioning earlier, but the value itself actually approaches infinity as time is at time t is equal to 0. So and of course you can see that where the one now comes in mathematically is at this point where we are saying that the integral from minus epsilon to epsilon, when you integrate the delta function, which is now looking for the area of this graph, then that is when you get a 1. So that is very significant, particularly with the expression of signals, and it is a very useful tool in defining when it comes to defining. Okay, like in sampling, we really use the unit impulse function to get a sample at a given time t or t naught. So having said that, so it is important that we have been able to know the physical meaning of impulse function, and now we can now say that an ordinary function which is everywhere 0 except at a single point must have the integral of 0. That is according to Liemann's integral. And therefore, we actually, from that statement right there, from this statement, we are saying that the unit impulse function is not considered as an ordinary function because it does not satisfy that that rule that is defined by Liemann's integral case. And therefore, we are saying that delta t cannot therefore be an ordinary function. And mathematically, it is defined by this equation 120. So, and again, in not so many words, we can try to decipher the meaning of this expression 120. That we are introducing now a general or a regular function phi of t, and we are multiplying it with the delta or Dirac function, and of course integrating it with respect to time from negative infinity to positive infinity. And we are saying that this integral will be equal to the function in the function phi t at time 0. So what that means graphically is this. This is time, and this is my function phi of t, and this is time is 0, 1, 2, 3. So we are saying that the integral from minus infinity to infinity of phi of t multiplied with the delta function integrated over time t is equals to the value of this function at 0. So if this function looks like that, this value here is equals to, probably if this value is 2, that integral will give us, what am I saying? It's going to give us a value of 2. So this simple integration simply tries to identify what is the value of the function, a regular function phi of t at time equals to 0. So I guess that makes sense, and that is what this equation 120 illustrates. And so we are saying that phi t is a regular function, continuous at time t is equal to 0. And that equation, I think we have well illustrated. And we have an alternative way in which you can express the unit impulse function, which is expressed in equation 121. And of course, you can look at that. We are saying that it is not defined. It is not defined at time t is equals to 0. Of course, if you look at this expression, we are saying that if you put that is our 0, then 0 is bigger than a. Which this means that a must be on this side, just probably a small distance from 0, and then b is bigger than 0, so it means that the b could be here. So we are saying that when we are trying to find the value of phi t for a is less than 0 and b is bigger than 0, then it is going to give us the value of phi at 0. So I guess that illustrates the first point, which I've already expressed in earlier on. But if 0 is bigger than both b and a, like if we now shift and say that let now, if we now, I'm trying to wrap, but I'm messing up my diagram. If you now say that from this diagram, my A is here and B is here and this is my 0, then we will see that we're not going to be able to find the value of phi okay, we're not be able to find this value because it is no longer meeting the requirement of being between the range of where 0 is defined. And again, you're saying that when both of them are 0, that both of them are at 0, again, you're saying it is not defined. So the point that this expression says is that delta of t will approach infinity at t is equals to 0. But now this function will approach, because I don't need to do that. This integral will approach this value at t is equals to 0, but it will be defined because anything you multiply with infinity becomes undefined. And that is the reason why our expression gets undefined at that time. And you see a slight difference when we are dealing with the discrete time signals, but for now, we will stop at that. So there is something that is again very, very significant that we should note from that, is that from that expression that I have stated before, that phi of t multiplied with d of t integrated with respect to time from minus t minus infinity to infinity, we have said that it is equals to phi of 0. What I'm trying to do here is that if I shift my delta function with time t naught such that I introduce minus t naught here, such that now this becomes minus t naught, then my expression will be evaluated at time t naught. So what I'm saying is that if t naught is equals to 0, then we are going to express our function at phi is equals to 0. If t naught is not equals to 0, then we are going to express our function at t naught. So t naught might be 1, might be 2, might be 3. So that is another very significant expression that we will use, because it traces the concept of shifted impulse function. So we can look at how graphically our function gets defined, and we can see that from figure 1.6, this is the unit impulse response that is defined at time is equals to 0. You see it is that this approaches infinity, but at time t is equals to 0. But when it gets shifted, then at time t is equals to t naught, then that is where our function gets defined, and you're saying that this value approaches infinity. And of course, I mentioned that the difference becomes when you integrate dt with time, then from minus infinity to infinity, that is the one that gives you a 1. And but again, the value itself becomes 0. So these are two items that we must get to the start, and we can now move on with that. So there's some additional properties of delta t, or the impulse function. And we're saying that if it is scaled, this is scaled by a factor. Of course, this is a scalar. So a scalar value that if you scale this delta function, that means it is equivalent to dividing by the magnitude of this scalar of the original delta function. And we will actually see that as we move on. Well, the other point that we are seeing about the delta function is that delta of minus t is equals to minus of t. So it is like it's an even function from what we said yesterday. And we are saying that if you define this value at t naught here, then if you have minus t naught at point, that my function will still be defined at that point, which is minus delta t naught. So these two are going to be the same. They are having the same value of infinity, but and the integral will still give us a 1. And last but not least, there is equation 125 that says that a multiplication of a function, a regular function, with the delta function is equals to the function at time 0 multiplied by the function at the delta function. And again, if you, without giving so many examples, if our function is looks for something like this, that is my function x of t. Of course, time is moving along that direction. So then we are saying that this function multiplied by delta t will have the value of x at point 0 multiplied by delta t. So that is the meaning of this second property at that point. And if we now were to look at to shift this t, again, it will still simply take that shape that we are looking at the value of the function at time t. So if this is my t naught, then we are going to be finding for x of t naught at that point, and then you multiply with delta t minus t naught at that point. So of course we know that the value of delta t naught, delta t minus t naught at that point is going to be infinity. It's approaching infinity, but then this value is defined as that value, and therefore that is the definition, or that is the illustration of equation 1, 2, 6. So equation this this equation 1 to 2 and 1 to 4 can be expressed as an integral, and this integral is actually referred to as the convolution integral. That says that the value of, or the function xt can be expressed as an integral of x of tau and the shifted value of the delta function with respect to tau. So it is like we are looking at the value of the function of that of xt at time equals to tau. So, well, I guess over time with examples that we shall be doing, we are going to find the meaning of these expressions better than we see them now. So then there is some generalized derivatives that that might be of interest to us, and I don't intend to go through them very much. The only bit I want to mention is that we can use the derivative as mentioned earlier to express delta function in terms of the unit step function, which is or a derivative of the unit function. I hope that sinks. So if our function is defined as this is my unit step function. This is time t, at this is time is equals to 0. If you differentiate this function, then it is saying that it is going to be equivalent to delta of t. So how we differentiate that is beyond the scope of this one. We are just saying that the generalized function can be used to illustrate the delta function. And I know we have skipped some theory up there, but all we are saying is that having said that, we are simplifying our earlier definition of unit step function to mean that it is going to be equals to 1 for t is bigger than 1 and 0 for t is less than 0. What this equation is not showing us is that at time t is equals to 0, what is the value of u of t? And clearly, that is not defined. And that is what we said earlier, that the unit step function is not defined for t is equals to 0. So that is what that equation illustrates for us. And I guess if you just take some time and try to understand the concepts that are being discussed in regard to the generalized the derivatives of impulse function, then it might make more sense to you. But all we are saying is that that the unit step function can be expressed as equation, that equation right there. So that covers the two signals that we have discussed, which is the unit step u of t, and we have also discussed the unit impulse function delta of t, and how these two are related, and this expression right here actually illustrates that, and it simply says that okay, clearly. I've muted people so that they don't unmute themselves accidentally like they have done. So we carry on. We have said that you can express, you can show the relationship between these two important functions, the unit step and the unit impulse. That unit step can be expressed as an integral of unit impulse as illustrated in equation 131. And this is the equation that probably you might need to remember. Otherwise, the derivations for me are not necessarily very important, because they just illustrate the last point, which is this expression like here. So, having discussed the two first signals, the unit step and the unit impulse, then we are ready to move forward and discuss the complex exponential signals. And to start with, we are going to express the function of x of t as a function of exponential, not exponential. This is the letter we call natural number. So and we normally call it the exponent of j omega naught t. So this is how you express the function of xt. And of course, the omega naught is the radiant frequency, and time, of course, is the one that we are discussing that is becoming the variant, and j is the complex number, or the complex. J, of course, is the complex number that is defined as root of -1. So this is how we can express the complex exponential signal. And we will see how this figure comes about, because in the next page, I believe, we are showing that we can break this function here into two values or two expressions. And we are, of course, using the Euler's formula. And therefore, we are saying that this function has a real part and the imaginary part. So we are saying the real part is a function of cosine, and the imaginary part is the function of sine. And therefore, this function right here is a combination of both sine and cosine. And as you can see, at time t is equal to 0, the function actually becomes more like a cosine than a sine, because we know that a cosine has a maximum at 0. So what we also see is that it is increasing in time. It is increasing in time because there's a component that you'll see shortly that is causing the exponential increase. Anyway, the exponential, when you are dealing with an exponent, and it doesn't have, it is either normally this is not how normally we do it. Ej omega naught t or e minus j omega naught t. So if it is having a negative, this is a decaying function. And if it is not having a negative at the exponent, then this is an exponential increase. And with that, we can simply say that because this is an increase function, because it doesn't have a negative, that is why clearly they are going to be increasing, because they are additive. They are you're keeping on adding the sine to the cosine and getting a higher value. But they decrease as you move towards the negative time. And of course, this other figure B shows an exponential decay or an exponential decrease in time. And of course, this is the one that you express as minus j omega naught t, where omega naught is the radian frequency. So I have actually included the Euler's formula here for the any person who might have forgotten how we break the exponent, the complex exponential value to the sine and cosine. So in our case, we had exponent of j theta, and our theta was ej omega naught t, and therefore that's why it is becoming cos omega theta plus j sine theta, and theta is omega naught t, therefore becomes cos omega naught t plus j sine omega naught t. And clearly that is the breakdown that we have done, and that serves to show how these expressions can be drawn in a diagram as we have seen in figure 17a and figure 17b. Of course, we are saying that the xt is a complex signal whose real part is the cos omega t and the imaginary part is the sine omega naught t. And an important property of the complex exponential signal xt in equation 132 is that it is periodic. And the fundamental period t naught of xt is given by this equation. So the very important point that we observe is that this signal is periodic and it has fundamental period t, and t is given by 2 pi over omega naught, and we know how we define omega naught, so we can replace omega naught with the 2 pi f naught. So of course these two can cancel, and we find 1 over f naught, and f naught is fundamental frequency. And therefore, you are from the fundamental frequency, you can always be able to show how the signal is repeating over time. And that's an important point to observe. So equation 134 illustrates the concept of fundamental period that is defined from the fundamental frequency or the fundamental radiant frequency. And we notice that xt is periodic for any value of omega naught. So that is what we say, that it repeats itself for even in the value of omega naught. And that is a very important point, because you observe that in discrete time, this is not true. This is not observed. So this applies for the continuous time, but for the discrete time, this does not apply. So very quickly, we jump to the general complex exponential signals. And now we are saying that xt can be expressed as a more general complex value, where we are saying that, remember what we said earlier, that x of t is equals to ej omega naught t. This is purely imaginary value, and therefore it gives us the 2 cosine cosine of omega naught omega t plus j sine omega t. But then if this is not a pure imaginary number, but it's a complex number, which might be s, that is equals to sigma plus j omega, that means that if we now introduce the time, so we are going to be having x of t as equals to e of s of t. And when you break that using the Euler's formula, you get that it has, okay, first of all, we say E is equals to sigma of t dot E j omega of t. I've just broken the s down because s is defined as that. And therefore, because this is a real value, so it is just going to remain as a real value when we break this down. So we are going to end up with E sigma t into bracket cos omega t plus j sine omega t. So we have this value that now comes in significantly.